All right. So thanks for letting me speak here. My name is Adam Heiniger, and among other things at Toptica, I am an ultrafast application scientist. And I want to be clear that that means that I know a lot about our lasers and how they work, but not a lot about neuroscience. I definitely would not call myself a neuroscientist. I barely know the difference between a neuron and an axon and this kind of thing. But I've prepared this talk. Hopefully, what I'll talk about as it relates to neuroscience isn't too basic, and what I talk about with lasers isn't too complicated. But please let me know if I need to recalibrate here, or feel free to interject with questions. So I'll be talking about basically the laser, the considerations you need to take into account when you're picking your laser for your multiphoton experiment, based on some of the goals that you have for that experiment. So first, let's start by talking about some of these limitations to multiphoton imaging. I'm sure that when you're planning your experiments, you start by thinking about sort of the demands of the experiment, how deep into the brain you want to image, the field of view, resolution, frame rate. And as I'm sure you know, all these things are limited by things like thermal damage, scattering and absorption in the medium, and background excitation. And of course, all those things are sort of related to each other either. Also, absorption in the sample by, say, water is what causes the sample to heat up, and that's what causes thermal damage. So the question is sort of how can you choose a laser that can, or how does your choice of laser sort of impact all of these things, and how does that relate to the experiment? So I'll talk about that. I also want to mention a little bit about maybe some other practical considerations to consider when you're choosing your laser based on the sort of the tension between reliability and flexibility of the source. And of course, always important is the tension between both of those and how much the laser costs as well. Yeah, and most of the neuroscience that I pulled for this talk comes from this paper from Chris Yu's group, talking about 3-photon imaging compared to 2-photon imaging and this kind of thing. I will be clear. I mean, obviously, I'm here. I'm a representative of Toptica Photonics, a commercial endeavor, but I'm going to try to be as sort of unbiased when talking about laser sources as I can be, to be as helpful as I can. So as I understand it, your goal is to deliver a packet of energy to a particular spot in the brain, and then maybe to scan quickly and do that at many different places in the brain without frying that brain. You want to see the brain operating while it's actually a live animal. And to do that, you need about 0.24 nanojoules for 2-photon microscopy at 920 nanometers at the focus, or you need 1.86 nanojoules for 3-photon microscopy at 1320 nanometers. The first thing that limits your ability to do that is the loss of that light as it propagates into the tissue. So this is, I think, another Chris Yu paper showing the combined effects of water absorption and scattering as you try to propagate into the brain, showing an attenuation length versus wavelength in the green curve here. You can plug that attenuation length into this exponential decay to say that if you have so much energy at the input of the sample, as you propagate some distance down, you end up with less energy. You can sort of flip that around and say that if you want to have the optimal pulse energies we talked about in the last slide at a given distance into the brain, this tells you how much you need at the input to the brain. So here we had, say, 0.24 nanojoules for 2-photon at 920 nanometers. As you go deeper into the brain, the amount of energy you need at the surface increases exponentially. This is the log plot, of course, so linear here is exponential. And then sort of that, so the attenuation length then that you get for 920 nanometers is on the order of 150 microns, and at 1320 for 3-photon is around 300 microns. And then that changes when you go from the cortex into the white matter as well. But this doesn't just scale infinitely. You can't put a joule pulse into the brain if you want to go really deep, because at some point you're limited by thermal damage in the brain as well. For 2-photon, we can argue with these numbers. Maybe it's 250 milliwatts, 3-photon, 150 milliwatts at 1320. So that kind of puts a cap on the power we can put on the brain. And we need to talk a little bit about how pulse energy relates to the average power. The average power of a pulse train is the pulse energy times the repetition rate. So we can take this curve we showed before, this exponential increase in your required input pulse energy, and just multiply that by the repetition rate to see how much power we need for a given repetition rate to get our target pulse energy at the depth we need it. And so that's what I've plotted here. And then I have this whole thing capped for 2-photon by our 250 milliwatt power limit. So I have to think through this plot even though I made it every time I look at it. But let's say we want to have, we're capped at 250 milliwatts. If we're using an 80 megahertz laser, then, and we want to deliver 0.24 nanojoules into the brain, we can either use an 80 megahertz laser, and we can get about 300 microns down with that 0.24 nanojoule laser before we get to 250 milliwatts. Or if we can somehow reduce that repetition rate to 20 megahertz, if the repetition rate goes down, then our pulse energy goes up so that we keep a constant average power. That means we can use that bigger pulse and get farther into the brain before we come down to 0.24 nanojoules. And another feature of this curve, it's important to note that if you can stay on this slope here, then you can do sort of the fastest possible imaging at your repetition rate, which is 1 pulse per pixel. But you're not just stuck there. You can obviously average over multiple pulses if you park your scanner at a single pixel and average over multiple pulses to collect the fluorescence excitation. But in general, it's better to be, you would rather have 1 pulse at 20 megahertz than 4 pulses at 80 megahertz. Because that 1 pulse will have, say, the optimum energy at your target depth. Those 4 pulses would have a quarter of your optimum energy. But this is a nonlinear process, a second order process. So you'll be getting a 16th of the fluorescence you need per pulse as opposed to a 4th. So you're better even at a lower using a lower repetition rate in optimizing with a single pulse for excitation. But this doesn't scale indefinitely. So we all know that single photon excitation is limited by this background fluorescence. You're exciting all the way down to your focal plane. The whole point of doing 2 photon is to remove this background fluorescence excitation, but it's not removed completely. Ultimately, at some depth, you'll see that the background emission out of focus is equal to your emission at focus, and that's for when your signal to background ratio equals 1. That's kind of your depth limitation for doing 2 photon imaging. And for 920 nanometers with GCamp, your depth limit ends up around 4 to 5 times your attenuation length, and that's about 700 microns. So I show that here, sort of with this depth limit on the plot. So there's not much advantage in going down to a 5 megahertz repetition rate, for example, because eventually you run up against this depth limit instead. This is the whole point of then going towards 3 photon excitation. It's a third order nonlinear process instead of a second order nonlinear process, which means you need higher pulse energy, certainly, but that means it's much rarer that you would have an excitation event outside of your focal region. And in that case, I think I've seen numbers that you're on the order of 9 times the attenuation length, so you can get to, say, 2.7 millimeters. So here I've combined all of that information into one plot, which is pretty busy, but I think we can all see what we're getting at here. We said our required pulse energies are, say, 1/4 of a nanojoule for 2p, almost 2 nanojoules for 3p. We have different damage thresholds for each one, and different attenuation lengths for each one. And if we put all this together, then you can see that for 2p, you can use 80, 20, whatever megahertz to get to this limit. But beyond that limit, you're going to want to switch to 3 photon. But even then, you're going to have to scale your repetition rate to get lower. And an issue, of course, with scaling your repetition rate is the time between pulses is the inverse. So basically, your period between pulses is the inverse of your repetition rate. So if you have a 100 kilohertz repetition rate to get really deep down into the brain, then that's going to be 10 microseconds per pixel, which is going to limit your field of view and or your frame rate. Okay, so that's, I think, most of the considerations that I would say to take into account when you're trying to reach a target depth. But that's all sort of the ideal case. Can you actually get the lasers you need to do this? If you look at a lot of the lasers that are available for 2-photon microscopy, they all have this base repetition rate of 80 megahertz. So how do you actually get the 40 or 20 or whatever repetition rate that you need? Sort of fundamental laser physics, the repetition rate, the fundamental repetition rate of the laser is based on the length of the laser oscillator. So this is a diagram of Toptica's fiber laser. It's a fixed wavelength ultrafast fiber laser. And it all starts with a ring oscillator at 1560 nanometers. And the repetition rate of a ring oscillator or a TISAF oscillator is given by the speed of light divided by 2 times the length of that oscillator. Solid state lasers, titanium sapphire lasers, are sort of free space optics, and it's kind of hard to scale that repetition rate by changing the length of the cavity going from 80 to 20, 80 to 20 megahertz, for example, you need four times bigger laser, and it's all free space optics. So I mean, you can kind of fold that beam path within a box, but it's kind of hard to do that on a reasonable size optical table. Fibers, conveniently, you can kind of just coil some optical fiber around and fit it into a small package. So this is one way that you can scale the repetition rates, reduce the repetition rates of fiber lasers. Of course, with fiber lasers or with titanium sapphire lasers, you can also put pulse pickers on the output. They have to be pretty fast if you're scaling down from 80 megahertz, because you want to be able to chop, say, individual pulses out. But it is possible, and even if you see on all of these laser company websites that they have 80 megahertz repetition rates, always feel free to ask if they can provide custom solutions at lower repetition rates. Toptica certainly can. What about the pulse energies? So if you look here, if you want with 2-photon excitation, if you want to get deeper into the brain, you need exponentially higher pulse energies. And are these things really available on the market? Most 920 nanometer lasers have between 1 and 4 watts of average power, and they have this base repetition rate of 80 megahertz. And that means that their pulse energies are, say, 12.5 to 50 nanojoules, and that's before the microscope. The microscope eats maybe 2/3 of the light, so you end up with something like 4.5 to 18 nanojoules at the top of the sample. So if we look at this exponential decay here, if you're at 4.4 nanojoules at the input, then you can get down to about 520 microns. 18 nanojoules, maybe 778 microns. And of course, you can integrate over multiple pulses as well if you want to go deeper. We said our limit is around 700 microns, so I think it's pretty reasonable to say that the commercially available 920 lasers can do what you need. And then 1320 nanometer lasers, these are typically OPO based. You start with probably a 1 micron fiber laser, pumping an OPO, which splits your 1 micron light into 2 photons. And one of them would have the energy corresponding to a wavelength of 1320 nanometers. And those systems often have higher pulse energy. You can get them between 400 and 600 nanojoules before the microscope. Again, your microscope eats some light. But according to this curve, this is on a log plot, you can see you can get down to sort of this 1.5 millimeter kind of depth. And again, you can integrate to go deeper, but this is sort of the limitations if you want to be at this fast as possible, 1 pulse per pixel imaging rates. But yeah, it looks like that the available lasers are able to do what you need them to do. Just a moment. So I guess sort of moving on from that discussion, were there any questions about sort of this balance?
Sorry, I have a curiosity question. Like what you mentioned, the microscopes eat up like about 1/3 of the energy. Is there like a specific part of the microscope that is responsible for most of it?
Yeah, it's a good question. I mean, you get some reflection off of every element, even if they are AR coded. It can be hard to get the broadband coatings you need at every optical element. If you have an AOM between your laser and the microscope for doing, say, power control or flyback blanking, then that maybe has 80% transmission. So in general, maybe your galvos don't have perfect transmission either. So I guess I'm saying microscope loosely, but it's everything between the laser and your brain surface.
Thank you.
Mm-hmm. And then the next thing I wanted to discuss is sort of this, I don't know how many of you wrestle with this, whether you should use a titanium sapphire laser or a fiber laser for your experiment. But fiber lasers have been able to access 920 nanometers for maybe the last 2 or 3 years. It's been a problem as long as I've been at Toptica since about 2013. We've wanted to find a solution to provide ultra-fast light at 920 nanometers because we're aware of how big this market is. But fibers typically have gain either at 1560 nanometers, where there's erbium-doped fiber, or at sort of 1050, 1030 nanometers, where there's a terbium-doped fiber. To get to 920, we had to figure out a bunch of clever tricks to manipulate our 1560 light and get it to high power at 920 nanometers. Other companies have found a gain medium at 920 nanometers and can make lasers directly there with fiber. But these fiber lasers are typically fixed wavelength. They're not tunable. They're a lot smaller than TISAFs. They can be a lot more reliable, but there's a lot of trade-offs. And I've kind of tried to summarize them here in this table. When it comes to reliability, I mentioned that solid-state lasers typically have free space optics inside. and that can make them a little more susceptible to some environmental drifts in your laboratory. Seasonal changes can change humidity. There can be slight changes in temperature, even for pretty well-controlled labs. And this can cause some drift of the position of optical components. And this is why maybe once every year or two, you need to have a service technician come in and tweak up the system and make sure it's working optimally. Fiber lasers have most of the light path inside of fiber. It's also this integrated, very robust approach. And so they really don't need anything like service contracts. They don't really break. Maybe after 5 or 10 years, a pump diode dies, and that costs a few $1,000s to fix. But the reliability for fiber lasers, I would say, is excellent. Titanium sapphire lasers need water chillers, which can be big and noisy. Fiber lasers can really be cooled with fans and a control unit while you have a cold optical head sitting on the table. The biggest advantage, I would say, for fiber laser or for solid state lasers is that they are widely tunable from, say, 700 nanometers to a micron or even beyond that, so that you can hit many different fluorophores, and that kind of gives your lab a lot of flexibility for this or future experiments. Whereas the fiber lasers, you can really only pick a fixed wavelength. Both have pretty good beam profiles. Size of the laser, if you're limited in space, maybe it matters. One thing that might be interesting, and I don't know how important this is to everyone, but with fiber lasers, it's very easy to use a single oscillator and seed multiple different arms that have different outputs at different wavelengths. And those would all be inherently synchronized because they're coming from a single oscillator. Whereas if you want to synchronize, say, a photostim light to your imaging light, with a titanium sapphire laser, then you need to use some complicated locking electronics to lock your fiber oscillator at 1040 nanometers to your TISAF at 920. And I've heard that doesn't work very well. It's complicated. It's very convenient to do this with fiber lasers. But in bold at the bottom, I put, I think the two biggest points for comparison here is that depending on the titanium sapphire laser and depending on the fiber laser, there can be a factor of 2 difference in price, but there can also be a significant difference in the pulse quality coming from both systems. And I'm going to talk about the pulse quality a little bit more on this slide. Titanium sapphire lasers have ultra short pulses propagating in air most of the time, and so they have very clean pulses coming out that have pretty much all of your power sitting under the peak. So all the energy in that pulse is contributing to your imaging. Whereas fiber lasers have to go through a lot of glass, most of maybe several meters of glass fiber inside of that the light's propagating inside of. And then you get all of these unfortunate impacts on the quality of your pulse. So this equation is called the nonlinear Schrodinger equation, and it describes ultra short pulse propagation in a medium. And some important terms here you might recognize. This term here is responsible for group delay dispersion or group velocity dispersion. This idea that so glass has a different refractive index for different wavelengths. Your ultra short pulse contains a bunch of different wavelengths because it has a broad bandwidth, which means that light is going to move at a different speed depending on the wavelength. And that means that your pulse can stretch out inside of a medium. So you have to contend with that in a fiber laser. And the other important one to contend with is cell phase modulation. So in these fibers, you have, say, watt level power contained within the 10 micron core of a fiber. And that's very high intensity. And that can cause, say, at the input, your nice, say, Gaussian or Lorentzian spectrum. So this is the pulse spectrum. As it propagates along the fiber with nonlinearity, it can cause that spectrum to broaden. The pulse duration or the pulse shape in time is related to the pulse spectrum. So when you get this broad spectrum with all this strange structure in it, that can also appear on the pulse. This strange structure then can also appear on the pulse in time. And although it may be 100 femtoseconds at the full width half maximum or the 1/e² width, lying under the surface or at the leading and trailing edge of the pulse is are these weird ripples, and that means that some of that pulse energy is wasted at low intensity. So none of this light contributes to imaging. It only contributes to heating the sample. And that means that if you could have all that energy under the peak of the pulse, say your brightness is 100% in this example, if you have a 15% reduction in peak power due to some of your energy being at the wings, then your brightness is going to go down by 0.85 squared, which is something like 70%. Sorry, go down by about 30% in that case. So it's much better to have a clean pulse. A lot of fiber lasers have sort of this, either they say they're 100 femtoseconds and have some structure on the leading and trailing edge, or they get rid of this stuff by just having a longer pulse, say 150 femtosecond pulse. Toptica has developed a method to have very short, clean pulses at 920 nanometers, but that means that it's sort of complicated the way we do it. So ours is not the cheapest fiber laser as well. Ours is maybe 10 or 20% more expensive than the others. So these are some of the trade-offs to take into account. If you want to have just the cheapest setup, say you want to have, I don't know, something for high throughput or something in your lab, then maybe you want the cheapest laser and the cheapest scope. If you want something sort of intermediate, I recommend Toptica's laser. Or if you want, the cleanest possible pulses, then maybe you want a titanium sapphire laser, and if budget is no consideration. That said, it's also worth considering sort of some custom solutions. If you need, say you want to do imaging of multiple regions of the brain at one time. I mentioned how we can do the synchronization with a single oscillator, and you could have multiple output arms. You could have multiple 920 arms or a 920 and a 1030. We can provide different repetition rates, strange wavelengths. I guess my point here is that if there's something that you need and you don't see it on a laser company's website, then please ask. It might be physically impossible, and we'll tell you so. It might be possible, but require a lot of money and time to develop it, or it might be something that we already have kicking around in R&D, and we just weren't aware that there's a market for it, for example.